Hi everyone, today we are going to talk about Hartley Oscillator. Our group member is Mugan Raj, Muhammad Zulkarnain, Teo Ang Yong, Ng Yen Hong, and me, Cheong Seng Guan. First of all, let us start from definition. A Hartley oscillator is an electronic circuit that generates continuous sinusoidal waveform using an active device, combined with a tap inductor and a capacitor in a resonant tank circuit. It operates on the principle of positive feedback, where the tap inductor provides the necessary phase shift 0 degree or 360 degree to sustain oscillation at a frequency determined by the LC component. Hartley oscillator rarely used in modern appliances nowadays. So, why it's not used in modern appliances? The first reason is its poor stability. The frequency of Hartley oscillator drift with temperature and component aging, unlike crystal oscillator. The second reason is bulking components. Inductors take up more space than modern IC-based oscillators. The third reason is frequency limitation. It struggles at a high frequency gigahertz range where digital synthesizer excel. The fourth reason is manual tuning required. Adjusting inductors for precise frequency is harder than programming a microcontroller. The last reason is the noise issues. LC circuits are more susceptible to interference than quotes.
On these pages, we have the circuit diagram of the Hartley oscillator. Inside the Hartley oscillator, you have many electrical appliances inside, and one of them is the transistor. It amplifies the signal with a 180 degree phase shift. In the tank circuit, you have L1, L2, C, and a ground, which sets the frequency. Inductor and capacitor create resonance, adding another 180 degree shift for feedback. And for the R1, R2, and RE, it stabilizes the transistor operating point. And last but not least, the CC2 and CE, which block the DC while allowing AC feedback and bypass RE.
First, let's look at the startup condition of the Hartley oscillator. When power is first applied, small random electrical noise from the environment exits the LC tank circuit. This can also be measured using a signal generator. Part of the output signal is feedback through the inductor L2, and importantly, it is in phase with the input. This feedback reinforces the signal. Because of this positive feedback, the loop gain increases and causes the amplitude of the oscillation to grow quickly. Now, moving to sustained operation. As the signal continues to grow, the transistor's nonlinearity kicks in and naturally reduces the gain. This helps balance the circuit. At this point, the feedback exactly compensates for the energy losses in the LC tank circuit, and the system reaches steady oscillation. The LC tank also acts as a filter, removing harmonics and giving us a clean sine wave output at the resonance frequency. However, in real-world conditions, the output voltage might slowly decrease over time due to energy being lost from the load resistor draining some of the power.
In here, we have the important formula of Hartley oscillator. For the total inductance, we can separate it to L1 plus L2 will become total inductance L. And for the resonant frequency, the formula was 1 over 2 pi square root LC. And if you sub the total inductance formula inside, the frequency formula will become 1 over 2 pi square root L1 plus L2 multiplied by C. And for the guarantee startup, AV multiplied by beta must equal or more than 1.
Now, let us move forward to application of Hartley oscillator. Hartley oscillator can use in radio frequency, RF transmitter and receiver to generate carrier wave for AM or FM broadcasting. It also used in signal generator to produce adjustable high frequency sine wave. Next, Hartley oscillator also used in inductive sensor and metal detector for detecting changes in inductance. Last but not least, Hartley oscillator used in Doppler radar and pulse radar circuit for generating high frequency signal, which is important in radar system. This is our reference. That's all from us. Thank you.